Hello, I'm Michael Hackney, and today I'm going to start a series of mini tutorials on how to use the new tuning wizard in KISSlicer 1.6. So stay tuned. KISSlicer 1.6 introduced a new feature called the tuning wizard. And basically what the tuning wizard does is simplify the process for tuning your printer for a particular material to get absolutely the best print results. By that I mean minimizing stringing and blobbing on the part due to excess filament ooze and things of that nature. The wizard itself is available up on the menu bar, so there's a wizards menu item now, and if you click on that and select tuning wizard, you'll see this dialog pop up. And the tuning wizard configuration dialog basically walks you through the process of tuning the various parameters, as we'll see here in a moment. When you click on the parameter to tune pop-up, you'll see that there's already presets for temperature parameter, for flow rate, for the new preload VE viscoelasticity coefficient, and for the destring length. Destring is called retract in other slicers. And then there's a sort of generic tuning value that you can tune other things that you may be interested in. We're going to primarily focus on these first four because they're the ones that are most important for your print quality. And that's why they're pre-packaged here in the KISSlicer tuning wizard. There is an order that you want to tune your printer and material when you're first getting started, or even if you're an aficionado at KISSlicer like I am. I do recommend basically starting from scratch because the way KISSlicer 1.6 does things is a bit different under the covers, and you don't want to come in with any preconceived notions of how you've been doing things in the past. Let KISS do its job and basically see how it works, and I think you'll be very pleasantly surprised. So I'm going to show you how to do that too. You'll notice that it's ordered by temperature, flow rate, preload, coefficient, destring value, and that actually is the order that you want to run these the tuning wizard for these parameters. We're going to start in this first mini tutorial with getting things set up, talking about the tuning wizard, and then actually tuning temperature. And then the next mini tutorial will be on flow rate, and the third one on preload VE coefficient, and then finally end up with destring length. Temperature is most important because really, it is where you should start. It affects the viscosity of the molten plastic, which in turn affects flow rate and also affects the preload VE coefficient. So you want to make sure you get your temperature, configured and tuned properly first. Now, many of us have been tuning melt temperature, flow temperature, extrusion temperature, as it's called, for their filaments for quite some time. There are ways that you can do this using other types of models and manually changing the temperature in the G code to basically do what the KISS wizard is going to do for us automatically. But the KISS wizard really simplifies this process. So you want to start with temperature. Then you want to do flow rate, and again, many of us have been calibrating flow rate for quite some time, and there are ways using standard models that you can do this, but again, KISSlicer significantly simplifies calibrating your flow rate. Then once you've done those two, you're ready to basically calibrate the new preload viscoelasticity coefficient, which is really the magic in KISS 1.6 as far as I'm concerned, and really is the feature that is the killer feature of this new slicer version. And then finally, once you've done those three, we'll wrap up with kind of a fine tuning now with destring. And in fact, many times, it depends on the filament, but for filaments like PLA and ABS, the preload VE coefficient tuning is so good, you might find that you don't even need to use destring at all. For more elastic filaments like PETG and especially TPU and NinjaFlex, the Flexies, you probably will need to do a final touch-up with the destring. But that's what this is all about. Before I actually select temperature, I just want to give you a little warning. When I do this, the user interface is going to turn this bright yellow. Let's go ahead and do it. There we go. So now you can see everything is turned yellow, and in fact, you'll notice there's even a comment here. The horrible yellow color indicates that the exported G-code is affected. And what is meant by that is, when you set up the tuning wizard, let's say we're going to be doing temperature first, and I'll introduce the model here that we're going to be using in a moment. When you generate the G-code that you're ultimately going to print to measure to get the best Z height for the particular parameter you're tuning, KISS is actually doing a lot of things underneath the covers to turn off features like retract, depending on the particular parameter that you're tuning. And so when you're in this special sort of tuning wizard mode, you don't want to be generating G-code that for normal parts that you'd want to print, because it won't be consistent. You'll be confused by the results. So by using this bright yellow color, it's painfully clear that you are in wizard mode, and as long as you see that yellow, you probably shouldn't be slicing parts that you're just going to print for fun or profit or whatever, for whatever reason you print your parts. When you disable the parameter to tune by going to none disabled, everything goes back to normal. So the way to use this new tuning wizard is to pick your parameter that you're going to tune, in this case temperature. Everything is in yellow, so we're good to go, and keep it there until we're finished with this particular tuning session. So next up, we want to get a part. And KISS has actually provided a part called the KS_wizard STL, and here it is. It's basically a simple rounded cornered cube, if you will. And the idea here is that as the printer is printing each parameter, you don't want it slowing down and speeding up when it approaches sharp corners. You want it to kind of maintain a constant velocity as it's going around the part. And this rounded corner object does exactly that. So it's a great part. It's 25 millimeters tall, so it's not very large. You can print these things very, very quickly and get through the tuning process in record time. So that's the basic setup. The next thing, as I mentioned earlier, I'd really suggest starting with from first principles, starting from scratch. And the place to do that is with the other new wizard that KISS has introduced, the Profile Wizard. So if you go up to the Wizard menu and select Create Profile Wizards and choose Material Wizard, the Material Profile Wizard will come up. Now, we did talk about this and actually used it in the very first tutorial on getting started with KISS. We walked through all 4 of the new profile wizards, and basically these are starting points that you can use to generate a new profile for style, for support, for new printer, and for material, which we're doing here. And as you saw in that first video, I actually printed a non-trivial part that typically would have a lot of stringing and blobbing in it because it has some very thin pillar type of features that are problematic. I printed that part using the as-generated profiles from the profile wizards, and the part was really nice. So these wizards actually do a very, very good job, but they're a starting point, and you can do a little bit better by using these tuning wizards to kind of adjust things, and that's what we're going to do here. So for this demonstration, I actually want to work with PETG. So I can go up to the drop-down menu for material. You notice you have a lot of different materials you can choose from. Or if you have an other, you can select it and just kind of manually set things up. But we're going to go with PETG. I typically print my PETG at 230 degrees, and that's the default value that the Material Profile Wizard is coming up with for me. But as you know, we're actually going to be fine-tuning that with the parameter to tune being temperature in our tuning wizard. So let's leave it at 230 for now. And bed temperature, I don't know why 87 comes up, but I'm printing on PEI, and I'm printing on a 70-degree bed. My filament is 1.75 millimeter diameter, and then I only have one extruder, so this material will be an extruder 1. I have no heated chamber, and then I'm going to call this wizard.petg, just so I know that this was generated from the wizard, and I'm going to click Create. And now we see down here in the KISSlicer settings, it has chosen the wizard PETG for me. I see the parameters I filled in, the 1.75, the 230-degree temperatures, 70-degree bed, and that's that. We do want to take a look at a couple of other things. You'll notice that it's already set a default preload VE for me, and that's convenient. Many times this preload VE, depending on your system, will work just fine. But in our case, we actually want to fine-tune it a little bit more, or at least validate that this is the best value to be using. And that's what this exercise is going to be all about. Calibrating temperature, calibrating flow rate, calibrating the preload, and then calibrating the destring, which you see here has already been set to 1 millimeter as well. So we're going to tweak all of these as we go through the calibration wizard. So that's basically it for the material. We're going to leave that alone. Now we're going to go over to style, because there are some style attributes that KISSlicer recommends when you're doing these parameters. So for instance, for the temperature parameter, if you read over here, it says, firstly, you must have warm same extruder and cool same extruder G-code defined. So if we go to printer G-code and click on warm same extruder, we see we have some G-code defined. In cool same extruder, we have G-code defined. If you use the printer calibration, or the printer wizard, profile wizard, it will actually do this for you. If you've got a profile for a printer that doesn't have these in it already, you can actually just click the tab that you're interested in, click on defaults, and it will generate some basic defaults for you. So you'll get your warm and cool same extruder G-code defaults that you need. So that's that first requirement. The next one is on style. And it says try a style with profile, style profile with 1.5 loops. So here's 1.5 loops. In vase mode, so I'm in vase mode, with a skin thickness of 2 layers. I'm using a 0.4 millimeter nozzle. I like to print 0.2 millimeter layer thickness with that. And so 2 layers of skin would be 0.4 millimeters. So I've set my skin thickness to 0.4 millimeters. And it says use the same rounded model that you would use for the preload VE test, which is this particular rounded model. So that's it. I do like to drop the seam depth and the seam gap down to 0 for this. I do like to set the angle to the front, and you see the red line there. This way you can see the seam where the beginning and ending of perimeters occurs while the thing is printing, and kind of watch what's going on more closely because you're facing it. Set the jitter to 0, so that seam will ultimately appear right down the middle. Not so important for the temperatures tuning, but for the other tuning parameters, you will be looking at that start-stop seam for each of the perimeter lines, and so having it facing you and with a 0 jitter right down the middle is required. Let's see, what else do we have here? Extrusion width 0.4. My extrusion width up here is 0.4. Turn off crowning, not important for this anyway. And let's see, perimeter first, and then finally turn off join loops. But again, since this is going to be printed in vase mode with a single perimeter, those attributes aren't really even going to come into play, but I do like to set them to this because I use the same style for some of the other profiles, the tuning profile parameters that we're going to do. I'll also post a link to this wizard temperature style, so you can just load it and get it automatically. So there we have it. Now the last thing we need to do is to configure the tuning wizard start value and end value. So remember what the tuning wizard is doing. As it's printing this part, it is going to vary the, in this case, temperature from the value that is at the z equals 0 up to the value at the top. Now, you can do it reverse. I could go from the hotter temperature to the cooler, or the cooler temperature to the hotter, and there are probably arguments to be made for doing it one way or the other for each of the parameters to tune. For temperature, it's pretty clear. You want to start with a cooler at the bottom and the hotter at the top. So how do you pick that start and stop temperature, or top temperature? Well, we know that our sort of default extrusion temperature is 230 degrees C. And so I'd like to have a little bit of a range around 230 degrees so I can, maybe pick a better value. So I like to go down to 220-ish or so about 10 degrees. and then at the top, maybe 240. Okay, so what this is going to do when I slice and print this code is going to start with 220 degrees at the first layer, and it's going to gradually increment the temperature as it goes up, 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 until we get to the top layer, which will be printed at 240 millimeters. Now, in the case of the temperature parameter, basically the help here tells you once the test is done and the part's cool, this is important, make sure the part is completely and fully cooled. You can use pliers, but really all you need to do is use your fingers and squish the part a little bit across the corners to check the interlayer bonding strength at various Z heights. And a little bit of subjectivity here. What you need to do is pick a height that shows good surface quality, which actually is not so subjective because you'll see if there are any glaring problems, you'll see where those are, but there will be a larger region that's got a pretty nice surface quality. And you'll want to make sure you get strong bonding, in that region that has good surface quality. And that's a little bit subjective. It's not a precise art anyway, and this will get you much, much further along than just taking wild guesses or using the filament manufacturer's quote recommended unquote extrusion temperature, which more times than not are significantly higher than they should be. And just to get on my soapbox about that a little bit, the filament manufacturers, really their primary concern is to make sure you can get the filament extruded through your hot end, your system, and not worry too much about blobbing and stringing of your parts. They figure you can figure out how to tune that out later. So they arbitrarily use, as a sweeping generalization, there are some exceptions, but as a sweeping generalization, they will publish extrusion temperatures that are significantly higher than you need. I've seen, just generic PLAs say that they need to be extruded at 220 degrees C. I literally just helped a person on, I think it was one of the Facebook groups yesterday, who was printing parts at the recommended recommended unquote 220 degrees temperature for PLA, and was getting all kinds of stringing and blobbing. And so I recommended that he start at 195 degrees, which is my general go-to temperature for PLA, and a couple of other minor tweaks. Print the part and see what happens. He did, and reported back that it completely eliminated the problems that he had. So there you go. 220 degrees was way, way too hot. So, rather than rely on the manufacturer's quote recommendations, unquote, use the KISS tuning wizards to actually find out what it is for yourself and for your particular printer and conditions, and you'll get much better parts. So into soapbox, here we go. So we've set the temperature at the base, the temperature at the top. We've configured our style, and we're ready to go. Let's go up here and click on Slice. The part is going to be sliced. No real magic there. Take a look at the part. Basically, it is just simply a vase. And now we can save the part. And I'm going to save it in the tuning G-code. And I like to give my tuning G-codes kind of a name, a systematic name that I can use to remember what I did in the future. So I'm going to click on this one because it's already mostly named, but I'm going to change the TPU to PETG. And of course I have to change the temperature range from 220 to 240. And there we go. We're going to click Save, and now I have saved the G-code for this part. I'm still in the tuning wizard mode. We're still yellow. And so the next step is to basically load this into my printer, get everything up to temperature, print the part, and come back and we'll take a look at that part and figure out how to determine what this best Z value is. And that will do it for the temperature parameter. So I'm going to go offline here for a few minutes and come back with a completed part. Talk to you in just a few. Okay, the part has finished printing. I've waited for it to cool. I've carefully removed it from the build plate on my D300 VS Delta printer. carefully taken some photographs of it, and here's a photo of the finished part. So, a couple of comments. Firstly, when you're looking at the part, just with your naked eye, it's very difficult to see a significant difference in the surface finish along this surface. However, when I put on my magnifying headset, which, let's see, maybe see these here, I can actually put these on, I can pick up the part, and I can scrutinize it in excruciating detail, or use a magnifying glass and take a look at the part. You will actually see some interesting things. You can almost see right here just a little bit of a layer separation. And then when it gets up in this region, really nice looking surface finish, nice and tight. And then when you get up here a little bit, and not only tight, but you also get just a little bit of definition on the edges of the layers. And then as you get up here, those layer edges start to get blended together and rounded over a little bit more, sort of indicative of excess temperature. Whereas when they're just kind of crisp and look like what you would expect the edge of a layer to look like, this region right here was just about right. So I'm going to use this green arrow. This is Z equals 0, which was 220 degrees C. This was 240 degrees C. And as I moved it up, move up, right here, definitely not good in these bottom layers. I actually squished the part by squeezing it on diagonally opposite corners, and it fractured right where I see that oddness. And then I could use, a pair of pliers or tweezers and just start chipping away at the layers up and up. And, the first few layers around here were brittle, but then it started to get really strong and almost impossible to break without a lot of force when I get up to about this region here. So kind of the minimal point of where things start to break or whatnot. I measure that, and it was like 9.8 millimeters, something along those lines. So, I mean, I don't even think you need to be that precise, because we're talking about typically, 3 degrees to 5 degrees is more than adequate for tuning your extrusion temperature. So let's call it 9.8. I'll go up here and enter 9.8. Hit return, and we see that my best temperature value is 227.84. Well, guess what? We started at 230. This isn't a terribly precise science here. There's a lot of subjectivity. A couple of half a millimeter, one way or the other probably is not going to make, a big difference. So 227 to me is basically 230 degrees. So I would round this up to 230 degrees. I would never round it down to 225, simply because going down in temperature, you actually may introduce problems, particularly when you start printing it at higher flow rates, things like that. So round up to 230. You would enter 230 into your main temperature, and probably your first layer temperature as well, unless you were doing something fancy, which we'll talk about in a future tutorial. And there you have it. Because this came out, kind of as I predicted, and also because, PETG is a pretty sticky material. So even at, fairly low extrusion temperatures, it's going to stick to itself pretty well. I really don't see the need to go in here and do a sort of a zoomed in, print. You might want to do that for PLA or ABS. Maybe even nylon, but for some of these more flexible materials like PETG and particularly TPU and NinjaFlex flexibles along those lines, probably close enough is close enough. If you were doing PLA, and let's say that I did want to, get a little bit more refined temperature gradient, here's how that would work. So my first quick and dirty came up with 230 degrees. What I would do now would be go in here and subtract 5 from that. So I would say 225, and I would add 5 to that. So 235. And then I would generate a new G code, save it, and print that, and then, again, look at the part very carefully, do the break test to try to determine where where the optimal melt zone is. And now, presumably if it's still around 230, it's going to appear about halfway up the part, somewhere around 12.5 millimeters or so, since it's a 25 millimeter tall part. But it might be a little bit above or a little bit below. But as you saw in the photograph, there's a fair amount of subjectivity to this anyway. So, being able to measure precisely a millimeter or even 2 or 3 millimeters up or down, probably not going to make a big difference. And it's not really going to make a big difference in the calculated extrusion temperature that you get here. What you're looking to try to do is to get in the ballpark with a well-considered temperature, and not be really far off. So for instance, let's play around with some numbers here. Let's say that I just picked 7. That's going to give me 227 degrees, not too far off. Let's say that I picked 14. So that's right around 230. So there's a fair amount of latitude, especially over this longer temperature range that I use for this particular part. Okay, so I had calculated the 230 degrees. I would put that into my material profile here. We're done with temperature tuning, so I could go up here and say disable. Close the tuning wizard, and now I'm back to normal, and now I've got a temperature calibrated material for PETG of 230 degrees, and I can either continue to use this material profile, or I could enter that 230 into my sort of standard profile. I'm going to come back and do the next tutorial on flow rate, where we'll calculate flow rate, and I'll start with this wizard PETG material profile because we've already got it, and the next thing we'll do is to calculate the flow rates, which are going to go into the minimum and maximum flow rate value here. But we'll talk all about that in the next tutorial. So that's it for now. Thank you very much.